Can you see the screen?
Not yet.
Yes.
I don't know why it is taking long. So you can see it now.
Yes, Prof.
So let's go through briefly data. What is data to a model? How you validate a model? Why we need to evaluate or to validate a model? Remember, one of the steps of modeling is validation, model validation. Before you disseminate the results, you have to confirm that. You have to prove that they conform to the biology of what you're modeling, or to the general structure of the biological process that you modeled. If not, then you cannot implement. You have to go back to literature. So how would you evaluate assumptions, or why do you need to evaluate your assumptions? Evidence for assumptions can be collected through methods such as interviews, focus groups, and/or surveys. So if you need to validate something, you set up your questionnaire in such a way that you have targeted questions for each of the assumptions that you added to any of your models. So you can use different methods, but you need to set it up in such a way that you have questions that target your particular assumption. So why is it important to evaluate assumptions? If you're questioning your assumptions, like the 3 different scenarios I presented for the dead people due to tuberculosis, you have to know why you need either. So if you question your assumptions, that if I put this dead class in the model, I'm assuming that all the dead people are kept in one place. Is it important to tuberculosis? No. Is it important to Ebola? Yes. So when you question your assumption, it helps you develop your critical thinking skills. And critical thinking involves analysis of information, evaluating evidence, and considering alternative possibilities. So whenever you question your assumptions, you learn to analyze information more carefully and consider alternative possibilities. So why do we need data for our models? Why do we need to work with models? To work with data. One is to describe the real patterns, and you solve real problems. If you have data, is that you can relate your model to the exact process, the real world problem. You can also test assumptions, and you can get more attention for your work. I think as I came in, you had a discussion where we were being told that it's very important to work with policymakers. But policymakers, you don't just go and give them your mathematics or your statistical results without relating them to the real world. So it is very important for you to get attention to your work. You must have data, and for you to have data, you can easily validate the results you have got, whatever method you have used. Then you can easily influence public health policy. So use the available data to fit into your model. You validate your assumptions or evaluate them, and then you can easily turn them into policies. What are the challenges of working with data? If you don't work with policymakers, definitely you cannot get good data. It is always hard to get good data sets. And we know the real world is messy. And when you go to the underdeveloped countries, we don't really keep data. We don't have that systematic way of keeping data. But in some developed countries, they do. So when you add the mess in real world, sometimes it is hard to understand the process. So if you have such a situation, then you're going to have challenges of working with the data that you've been availed with. So I know you use statistical methods or nonlinear models. They can become very complicated if you have data of one thing. Now, when you look at that tuberculosis model, What data are you going to collect? The one for people on Y dots, the ones who are exposed? How do you know that somebody is exposed? Most of these classes we have of the models, there is no line. You cannot say that tuberculosis exposure is set 2 days. You can't say that at the end of the 48 hours sharp, an individual is going to change from E to I, because there are so many other things going on into this person. There is immunity. How does the immunity of that person respond? What is the general behavior of that person? So it is very hard to relate mathematics to the real world situation without data and without assumptions. And you have to understand that even the methods we use are complicated. So you have to understand all this and put them into perspective. So what about pure theory? It is valuable for clarifying concepts, developing methods, integrating ideas. And the world, we need a few brilliant theorists and many strong applied modelers. So it is important that you can come on board, but you have to understand that the processes are quite messy. There is no line between one transition. There is no single line between a transition and the next. You can never tell when somebody becomes recovered. You only assume there may be 7 days and take a wise guess that maybe after 7 days, this person should have recovered. But you've seen people who have a disease for 2 weeks, even if it's malaria. Then some will have it for 3 days. But it is important when you have the data, because then it simplifies all this mess going on within individuals. So what do we need data, or what is needed to build a model? You can have individual clinical data. That is the latent period, that is time from infection to transmissibility. You can get data on infectious periods, that is the duration and the test of shedding. That is in the infectious diseases. You can have data on immunity, how effective and for how long. You're talking about the TB model, moving from R to S. How long does it take to do that? Is there a clear line from infection to treatment that you'll know every 1 day or every this number of days an individual will move from R to S? Then you can also use population data, that is population size and structure, birth and death rates, survival, immigration and immigration, the rates of contact within and between populations. Within a population is now you in a College of Health Sciences. Between population is now you with the entire university. So you can get this data, and you know the data sources for each of the different data that we need. Then the epidemiological data, that is the transmissibility. For example, what is R0? What is density dependence? Do transmission depend on density or on frequency? That is frequency of interaction. Is it frequency dependent? I know we did this, and I know about this yesterday. Is it about the density of the people who are infected with tuberculosis, or is it about how many times you interact? Then of recent, we have these climate or environmental factors, the seasonality. We know that during rainy season, some diseases transmit higher than during the sunny seasons. So when you factor in seasonality, where will you get the data? What kind of data do you need? If you're looking at malaria, for example, you're going to look at forestation data or deforestation data. You're going to look at how much rain you get, what is the temperature, because you're thinking about the mosquito and where it breeds. If you're looking at tuberculosis, how does climate or seasonality factor into your tuberculosis? So what do we need to validate a model? If you have time series, then you're going to need the instance, that is the number of new cases. You also need prevalence, like the proportion of the population with disease. If it is zero preference or zero instance, you have to show the individual's history of exposure. If you're looking at age, sex, spatial structure, that is if you have it, then you're going to look at the mean age at infection. And all these can be used to estimate R naught. And if you have cross-sectional data, you have seroprevalence survey or the prevalence of chronic disease, the endemic disease that is at steady state, gives you insight into mixing, epidemic disease, the outbreak size, the attack rate, and the different risk groups. And I know you did, I don't know if you did theories of biostatistics, where you look at the measures of association and so on. So how do we validate models, or what is model validation? Now, in this step, or in the validation step, the formulation is interpreted back in terms of the physical structures of the problem to yield the behavior of the mathematical model. You interpret your model into the physical structures of if you're modeling tuberculosis, you have mathematical results. What do those mathematical results mean in tuberculosis language? So the behavior of a mathematical model is then compared with that of their given problem in terms of the data of the real world to determine whether the two are in reasonable agreement or not, according to same predefined criteria. And this is what we call validation. And you need to know that the criteria for validation should be chosen with care. It depends on the data you're using, it depends on what you're doing. If the criterion is too stringent, that is, if it requires a very good agreement between the model behavior and the physical world, then the resulting model will be very complex. If you need your model to imply as close as possible to the real world, then you're going to add in a lot of factors in your model. If less stringent model, then you need a model based on a coarser system description. And in general, you have to start with a fairly stringent criterion, and then you simplify. Otherwise, based on the degree of disagreement, either the criterion may be weakened or the model may be made more complex. So you have to balance, you have to know what you need and how to get it without making stringent requirements or setting stringent conditions, and without you simplifying the model so much that it no longer conforms to tuberculosis, for example. So this is the usual model structure or the modeling process. You start with a real world problem. Now you know the real world problem for example, you have tuberculosis. You make simplifying assumptions. You have the real world model. Now this is mathematics. After you do that, you formulate the model, you analyze using mathematical language, and you interpret. So the validation takes place here after you have analyzed and you're interpreting results. Do they conform to literature? Because for every problem we come across, there is always literature behind it. So do your results, your mathematical statistical results, conform to the literature of that disease, for example, tuberculosis? Are they in line? If not, then you're going to validate. You test with the real world. If it's not, then we have steps you use to validate the model. So assumptions and validation. The mathematical structure assumptions involve additivity, divisibility, certainty, and proportionality. Certainty is probability. So these assumptions, when severely violated, will cause validation tests to fail, and you must then consider whether they are the cause, or whether they are the cause of failure. So if so, the use of techniques such as separable, integer, nonlinear, stochastic programming may be desirable to construct a new model. We have had cases where you need to go back to literature and reconstruct the model, because the model you have doesn't really conform to literature. You also have to be careful, because we had a student some time back when HIV was still a forbidden topic, whose model told them that if you need to solve HIV, you're going to kill everyone with HIV. Now, it works with other diseases where you do culling, but you can't make a recommendation that you should kill everybody. So a model that tells you to kill everyone is unethical. Although if it is something else, or if it is applicable to something else that is not a living organism, it might work. So as you validate, you have to be very careful that at times you might have to go back and construct a new model. So modeling assumptions may also lead to validation test failure. The assumptions that you make can lead to the validation process to fail. These assumptions embody the correctness of the objective function, the variables, equations included, coefficients, and equation specification. Your assumptions lead to a particular model. You can have the same problem, but because you're making different assumptions, each one of you will have a different model. So programming algorithms are quite useful in discovering assumption violations, and given an optimal solution, one may easily discover what resources were used, how they were used, and their marginal values. Thus, when presented with an invalid solution, resource usage and resource valuation should be investigated. Models are most often invalid because of the inconsistent data, bad coefficient calculation, bad equation specification, or incorrect objective function. All these, apart from the data, are to do with the assumptions that you make. You can make a model invalid because the data doesn't fit that model. But the data doesn't fit the model because you made some assumption that doesn't conform to what you're modeling. So what are the steps in validation? Step 1, you alter the model variables, equations, and data to reflect the validation experiment. You order the model variables, equations, and data to reflect the validation experiment. And this you can do one at a time, or you can do all at the same time, although each method has different shortcomings. Then when you do that, you solve the models. You evaluate the solutions. Is it infeasible? We usually say, is it feasible? Is it bounded? Is it optimal? In other words, feasibility can mean biological, it conforms to biological meaning of your process. Is a solution bounded? If a solution is not bounded, then it means that if it is COVID, it means it is going to attack everyone and perhaps wipe out the entire population, or it will continue forever and ever. Is it optimal? Optimal means maybe what is you have utilized all the resources that you have and you have attained the maximum out of it. So when you have an optimal solution, it means it suffices to fulfill your objective. And the question I have is what I think the algorithm, let me see the question. Programming, for example, your R, you have to write a script in R, that is programming. So how you write that script will give you the output. So programming algorithm is the script that you write in either software you use to give either to fit the data or to simulate and have for you to have solutions. So step 4, if the model variables exhibit a sufficient degree of association, I know you did degrees of association in biostatistics or in theories of biostatistics, then do higher level validation experiments or determine if the model is valid and proceed to use it. If the model does not pass the validation test, then consider whether the data are consistent or correctly calculated. The model structure provides an adequate representation of the real-world system, and the objective function is correctly specified. So if the model doesn't, is your data consistent and correctly calculated? Some of the parameters we use in the models are estimated from the data that we have. So how did you do that? And is that data, when they were collecting the data, do you think, especially if it is prior secondary data, Do you think they made the same assumptions that you made when you're constructing the model? Does the model structure provide an adequate representation of the real-world system? Is it really a tuberculosis model? And the objective function, especially if you're looking for optimal results, you have to have an objective function. Is it correctly specified? Then you need to fix the model. Then how would you evaluate the solution that come out from the model? If the model solution is infeasible, examine the results to find the cause of the infeasibility. Use the artificial variables best. Use the artificial variables. Okay, I saw a comment. I thought it was a question, but they are describing an algorithm. I gave you the mathematical definition, short and simple. So if a model is not feasible, you examine the results to find the cause of infeasibility. Examine your results. Maybe you have singularities. Maybe it tells you people are not dying, but you assume the people are dying. Usually you get you can interpret your results in the language of what you're modeling. You can say this result means, for example, people with tuberculosis are not recovering, but in your model you have that they are recovering. Then you have to go back. You use the artificial variables and you determine what is the problem, what is the cause. Then you go back to the origin, to the previous step. If the model is unbounded, use the large upper bound method from the last, that is in the 5 steps. That is, use one of the, I can share the steps with you. Then use a larger upper bound, and once the cause is found, you go back to step 6. If the solution is optimal, perform association tests. I think you know how to perform association tests. There are so many different ways how to perform association tests. For example, regression models. You can discover the degree of correspondence between the real world and the model solutions. You can also perform tests to look at the prime and dual variables. I don't know if you did this in statistics, but you can find this in theories of biostatistics, where you go into the theory behind the applicable biostatistics. So association tests can be used to measure whether a set of model results are similar to observed results. There's a couple of them. I think you are aware of those tests. Then what are the possible problems that can cause failure of validation, or can cause failure of a model to conform to literature? For example, the number of basic variables is limited by the number of constraints. Overly simplistic models will lead to limited solutions, that is, over-specialization. The objective function may be misspecified. When I look at the tuberculosis model, I don't know what the objective function was, but if I want to minimize death, for example, maybe I want to minimize death, but then as you fit data, you're doing anything else apart from different ways you can minimize death. Then too much aggregation in time may cause problems. So assuming you're looking at this tuberculosis, or you have large time periods between the different steps of your model. So you can make them, you can disaggregate. Instead of looking at, for example, the tuberculosis model, you have S, E, I, R, and D. You can disaggregate. You can add, I don't know if in that model you have a class that is on treatment. You can disaggregate and have people on treatment, maybe people who fall out of treatment, people who continue with the treatment. So you can break down the I class into further compartments. You disaggregate such that you shorten the time between an infection and death, or infection and recovery. Then perhaps you'll get more results out of the model. So if you've done all this and the validation tests still fail, then do demonstrations with an invalid model, that is assuming this is an approximately correct structure. You just use an invalid model and see what it gives you. Then or you can abandon the project, or you limit the scope of validation to a lesser set of variables. That is, you aim for a less strict level of validation, and then you will subsequently qualify the model to be used. But what is the implication to your objective? You have also to keep that into perspective. How would you fix the model? If all the variables have been fixed at real-world levels and still invisibilities occur, then the units of the inputs and outputs may be inconsistent. Maybe the data you have is per day, but in your model, you're running the model per unit per second or per month. If the data are accurate and the model structure problems are suspected, errors may have been made in constructing the matrix additional constraints. So as you constructed the model, maybe you made some errors in constructing the model. So you might need other constraints, for example, risk factors or willingness to adjust risk. You have to define your risk. Are you going to look at risk based on the age, based on the sex, based on the geographical location? It all depends. So you have to add in more factors into your model, and you re-specify the model. Once you do that, then you go back to step 3 in the previous not chapter, in the previous section. You go back to step 3 and repeat the validation process. Then comments. Validation is important. A good model is validated by construction and by results. Construction means how you formulate, how you come up with that model structure. For example, that tuberculosis model, how did you come up with that structure? Then what results are coming from that model? That is validation. The ultimate test of validity is adoption of the model by decision makers. Once they pick up your model, then you know that you're validated. I think you use that statement that I feel validated because this model has been picked up. Just to share, when we were doing this modeling of COVID, we had to validate our model. We had to present the model to so many different people. But that model was made by policymakers, people from the Ministry of Health, people from, there were 3 sections in the ministry. We had the policymakers, we had the incident commander, that one who used to collect the data. We had the doctors who were attending to the patients. Then we had the procurement department. Then we had the mathematician. Then we had professors from the College of Health Sciences who know public health. So by the time this model came out, everyone had input. Everyone had input what they thought was required for the model. Even people at the borders to know how movement in and out was taking place, even with the lockdown, the porous borders, all the information came up. People from the quarantine. So we presented the model to so many different people. The last one, I think, was the London School of Health Science. I don't know if that is the title. But none of all those people ever added anything to the Ugandan model because it had captured everything. So just to stress the point that it is very important to work with policy or decision makers because they give you what they want. You just have to make a framework of what they have given you. Then you determine the output or your objective. So it is very important when your model is picked up by decision makers. So I'll just stop briefly on sensitivity analysis because I have to run for another lecture in the afternoon. Sensitivity analysis is also one way of determining how different values of an independent variable affect a particular dependent variable under a given set of assumptions. You change one parameter, then how big or how different or how small your results by just changing this one parameter. So as you do that, you're trying to see how sensitive your model is to that one thing that you're looking at. So in other words, you study how various sources of uncertainty in a mathematical model contribute to the model's overall uncertainty. If you're uncertain about death due to tuberculosis, how does it affect your model? So that is sensitivity analysis, which is also important because if you're looking at control, or if you're looking at treatment or any other method that controls the disease, then you can know that this parameter is very effective in controlling or in reducing the number of infected. This one is not. And also it depends on whether the sign of this sensitivity is positive or negative. If the sign of the sensitivity index is positive, for example, it means as you increase that parameter, your output will increase. If it is negative, so that means if it is a good initiative, then you continue. If it is not, you're going to reduce that initiative. If the signs are negative, it means the more you increase, the more reduction you have in your objective function. So were you trying to minimize or to maximize? Then you're going to know that this parameter is not good. Then you have to evaluate or validate. So is sensitivity analysis important? Yes, because it will identify how much variations in the input values are for a given parameter, for a given variable impact. Sensitivity analysis is to identify how much variations in the input values for a given variable impact. For a given variable impact the result of a mathematical model. Sensitivity analysis can identify the best data to be collected for analysis to evaluate a model's results. By performing sensitivity analysis, you can determine what parameters you need to focus on for you to collect the required data. So it is basically a what if. Sensitivity analysis is what if. The what if analysis, that is, you assess the impacts for an output of a system by changing its inputs. You assess the impact for an output of a system by changing its inputs. If you change something small, what is the output? So that is sensitivity analysis. The methods you used in sensitivity analysis also vary if you're using, depending on the type of model that you have, stochastic, statistics. But now we have the most commonly one used is MCMC, Markov chain multi-carrier algorithms. You just have to input your model and data. You perform sensitivity analysis for all the parameters, one against the other, two against the other, and so on. So what you need to answer when you're performing sensitivity analysis is if these variables deviate from expectations, what will the effect be, for example, on the model, and which variables are causing the largest deviations? Which variables are causing the largest deviations? And the other question you have to ask yourself, are those deviations important to your model? Because you can have, for example, natural birth. You can have that the more people are born, the more the disease will prevail. But can you control natural birth? Are you in position to control birth of people? Are you in position to control people coming in? That you can control. Remember when they cross the borders, but you cannot control multiplication within the population. So you have to understand and to know where you have to make recommendations, especially if you're working with policymakers. You have to look to see where you have the largest deviation and if it is important or if it is something that can be implemented, especially unethical conclusions are a no-go area for modelers. You have to make conclusions that are ethical always. So there are two types of sensitivity analysis, partial sensitivity, and then the best case or worst case scenarios. Partial, you select one variable, change its value while holding the value of the other variables constant. Then the best case or worst case scenarios, you establish the upper, that is the best case, and the lower, that is the worst case, boundaries, for example, the cost-benefit analysis study. And this type of sensitivity analysis shows how a broad range of program or policies possible outcomes affect the bottom line. You can have different sets of parameters that can give you different outputs of different magnitudes. Then you choose which parameter works best for that particular scenario. And I think finally, to perform best case analysis, you use all the most favorable assumptions. For the worst case analysis, use all of the least favorable assumptions. So I think I've talked about the importance of assumptions, the validation, and then why we need sensitivity analysis. We have a question: what dictates the type of sensitivity analysis to employ? In most cases, it depends on what you actually need. For example, if I want to know the importance of a parameter to a model, I can just do it, and I can just use an analytical method. I just compute R and naught and then see if it is sensitive to that parameter. But if I need to look at sensitivity, I remember we had a paper on the strikes in Makerere University, and to determine whether the police or the leaders or the lecturers or the administration was affecting more or igniting more violence as the strike progressed, we've performed sensitivity analysis for all the four. So it really depends on what you want. Then if you want to know if you want to stop the strikes, what do you do? And the most easiest one was just getting rid of whoever was striking. So the method you use depends on what you really need. It depends on your model. You just have to understand what you need, and then it will dictate the method you use. If you have to compare all the models of a given parameter, and there are usually so many, then you're going to go from MCMC. And then you look at correlation and so on. Then the other question is, all this modeling seems to be about infectious diseases? What about the NCDs? Can modeling be done for them? If not, why? What is NCD?
Non-communicable diseases.
Yes, you can do non-communicable diseases. We have models on cancer, on diabetes. The only challenge you might have is the methods to analyze, because when you're looking at cancer, for example, you're going to go inside a cell. So you have to use tumor growth models. And most of these, you can use partial differential equations. So the difference is that you're going to go to the cell that is affected inside someone, and you look or you study the dynamics of that cell. Even that cell changes from a perfectly healthy cell to one that is maybe sick, then to complete failure of that cell or organ. So yes, you can, but you go inside someone and you look at the target cell. So you can model anything. Any other question? Okay, that's what I have to share. The other thing I saw was on I think practical sensitivity analysis using Python, but I had indicated that I have not used Python in a long time, and you need a model, you need data. So coming up with that, I didn't come up with any code in Python. So I guess they make the arrangements to have someone to do the Python part of it.
Thank you so much, Doctor. Maybe I need a clarification on something.
Okay.
Normally, when you want to validate these models, especially if you have used assumptions, you have to use data, right?
I mean, most of it.
Available data. What happens if you draw a model and you only use assumptions, but you fail to get real data to validate your model?
Then you can perform sensitivity analysis.
Okay, thank you.
For HIV, you know that the more, what example can we use? Let's use, because you can sleep with 100 people, but when you're protecting yourself, so that example will not work. But let's look at COVID-19. Remember, there was a time where we had to wear masks. So you can assume that the more people wear masks, the more likely transmission will be reduced. So you just look at that particular parameter for the rate of wearing masks. Then you perform sensitivity analysis on that parameter. When you increase it, does it increase or reduce? So you can do a sensitivity analysis on your parameters, but it is always nice. Or your statisticians, you can generate. Do you know artificial data?
You generate using MCMC.
Well, yes, or even R. You can run your model, extract the data from that model, then you disrupt the model, you add some noise. The type of noise you add depends on your model, but you can just add some noise to the data. Then you fit. When you disrupt by adding some noise, you're changing from the data you generated with your model now to uncertainty in the output. So once you add this noise, again compared to the artificial data you generated with your model, are they still in line? So I always do that when I don't have data, or when I cannot get data that is really meaningful to do any analysis. Just produce artificial data and then add some noise. Then rerun the model with the noise, and you fit it to the data you generated without noise. That means that any disturbance you have is either conforming to the original data or it is completely different. That can also work using artificial data.
So how do you conclude using either the data with the noise or the data you generated at first that your model is valid?
Now, if you add noise and the model still conforms, then that means your data is, not your data, your model is valid. Because even with disturbance, it's still conforming to the biology of the system. But when you have completely, data, of course you have to define how deviated you want it, but that's not problem. That's not a problem. So if it still conforms to that, that means even if somebody came to destabilize the system, it is still stable.
Thank you. That is clear, Prof.
Prof, a question here. You talked about solutions being infeasible, unbounded, or optimal. Do you have to always check for these three cases whenever you're doing a model, or it depends on which particular model you're doing?
Now, after you write your model, after you've come up with a model, when you have that structure, you come up with equations, you must check whether your solutions are bounded or not. Otherwise, if you're looking at, for example, HIV, you know the percentage of people in Uganda that have HIV. Let's say 10%, that's about 4 million. Now, if your model is running to 12 million, that is not correct, because the maximum number of people you have in Uganda with HIV are 4 million, but your model is unbounded. That means it is giving unrealistic results. So you must check whether the model is bounded. that means it remains in the confines how you defined it. This 2B model was a constant. That means the population is constant at all times. When you check whether it is bounded or not, and it shows that it is continuously changing, that is not right, then you go and fix it. So you must check whether it is bounded, then you get the solutions of your model. After you solve this, after you solve for the, at equilibrium, you know how to solve those equations. You find S star, I star, and E star, for example. You might have a negative solution, that S is negative. You don't have negative people. So your solutions must be feasible to the system. So you check for whether they are feasible, whether they are bounded. I don't remember what the other one was.
Optimal.
Yes, an optimal solution now is going to be if you have put in some interventions. Are you getting optimal results out of your using that intervention? Are you controlling infected people? Are you reducing on the number? Optimality is now something different when you're studying whether the intervention you used works or not. So optimality you don't, but feasibility, especially, that's why when you read these papers, you will say, since the solutions are both positive, therefore the model is biologically meaningful, because you're trying to determine whether it is biologically meaningful. You don't have negative people. These impractical things, you're ruling them out.
Okay. Thank you, Prof. That is clear.
Okay, so if we are clear now, I think I can wish you a good afternoon.
Okay, thank you, Prof. Is there anyone willing to help us give a vote of thanks to Prof. Betty for being able to give us such a wonderful session?
Prof, just a second. I would like to ask Prof to kindly share with us the model she had developed for us who had presented earlier.
Oh yes, if you can give me, let me share it again here. You tell me what you need to, what I missed out, because I know it might take you time to digest I used simple software we use in mathematics. Let me just share with you this model, and then you put this one. Then we can agree on what is missing. I put it there, then you can use the model. I hope you don't have to change it later on. Okay, so what is okay, so what is missing in that model? The recruitment, the constant recruitment, right?
Yes, Prof.
The mu that goes to S, and then the loss of immunity, the arrow from R to S, right?
Yes, Prof.
Okay. So let me just fix it, and then I share it. What is the email address? I hope I have your email address.
Doctor, also based on your explanation, I think we are also going to remove the D, because you said since it's not Ebola, perhaps the dead people are collected somewhere, and perhaps we need to ascertain the number of dead people. And this is TB, maybe the D will also be removed.
Maybe the D.
The D compartment.
Okay. So we remove the D compartment.
No, that's a
suggestion.
It's not from the group.
Yes, Doctor, we had thought about removing the D compartment and also splitting the I compartment.
The I, yes.
Yeah, into those ones who were receiving the dots and those who were not receiving the dots treatment.
Ah, okay. Such
Yes, so
that
that we,
different, such that you have different ways
so
of
that we, yes, of studying the recovery rate.
Mm. So if we remove the D, that means people are dying due to tuberculosis and then not going anywhere, right?
Yes,
Okay.
so that we leave the death from the eye compartment. We leave the deaths due to natural causes, and also leave out the deaths due to TB on the eye compartment, but still we split the eye compartment into two.
Into two. So that means I will have to change. You see that arrow that splits into two? We just split the compartment, right?
Yes,
Instead of, okay. So we have I on dots and then I no dots, right?
yes, doctor.
And you want to call it I dots?
I want to call it eye dots and eye no dots.
Okay, so I'm going to share it. I hope you have given me the email, right?
Yes, I've sent an email through the chat.
Okay, I hope I can still have it, but what you can do, you can email it to me.
Okay, Prof. Let me do that. Thank you.
Okay, thank you, Prof. I request Joanne Nanteza to help us give a vote of thanks to Prof. Betty.
Let me take this opportunity to give our appreciation for the wonderful session. I hope the session has become better modelers and to have you handled a very massive question of standards. This is something that we don't had an opportunity to raise. By the end of this session, we've been able to take one or two. Thanks so much, Prof.
Okay. All right, so if you can just send me an email for those of you whose model I have.